Hello and welcome to the second session of the series where we are dealing with managerial statistics using the R language. And in this session, we will be dealing with normal distribution and central limit theorem. Central limit theorem is a very key component of statistics as such, right? But to understand the central limit theorem, in this part of the video, we will deal with normal distribution. We will understand what is central limit theorem and we will talk a little bit about normal distributions. And in the next part of this video, we will go ahead and actually see the central limit theorem in action, right? So what is the central limit theorem, right? So central limit theorem is one of the cornerstones of any kind of statistics, managerial or otherwise. And it says that no matter what the shape of the population distribution is, the distribution of the sample mean will be approximately normal if the sample size is large enough, which is greater than equal to 30. And the mean of the sample means would be close to the population mean, and the variability of the sample means will decrease as the sample size increases. So what does it mean practically, right? It means that, see, in practicality, it is not possible for us to deal with the entire population, right? So we always work with the samples of the population. And what we usually need to do is we need to make inferences about the population from the sample, right? So how do we do that? Central limit theorem is actually a base for multiple ways that are there in statistics to do this. But what it basically says is that if I take large enough samples, right? And when I say large enough, it means of size greater than or equal to 30. If I take large enough samples from a population and I find out the mean of all of those samples, and I plot a frequency distribution of the means of those multiple samples, right? So if I take, say, 1,000 samples from a population, 1,000 samples from a population, I compute the mean of all of those 1,000 samples that I have taken, and I plot the frequency distribution of the sample means, then the resultant would be a normal distribution. Okay, so let that sink in, right? So what I'm doing, again, just for clarity, what I'm doing is taking 1,000 samples from the population, computing the mean of each of those samples, and plotting the frequency distribution of that means, right? That plot will be a normal distribution. And the mean of this plot or the mean of this distribution of the sample means would be equal to the population mean, right? So if I have taken 1,000 samples, I compute the mean of all of those 1,000 samples and I take the mean of those means, right? That would be close to the population mean. And the variability of the sample means, like how sample one means differs from sample 20th mean, and how the 20th samples mean differ from the 100th sample mean, will reduce as the sample size increases. If you take large samples, the means of all of the samples is expected to be closer to each other as compared to when you're taking smaller samples. Okay, so this is what the central limit theorem is. And like I said, it helps in making predictions about the population data. It allows us to use normal distribution formulas even when the data isn't normally distributed. This is important, right? Because it basically tells us that even if the population is not normally distributed, it's okay. If we're taking large enough samples from that, we could use some of the assumptions and some of the formulas of normal distribution, and it forms the foundation of the confidence interval and hypothesis testing. So we will see what central limit theorem is, but before that, let us talk about little about the normal distribution, what it is exactly, right? You can ignore this. This is just a way to set a seed for random number generation. So, when a random number is generated, it is an internal process, right? And uh, setting a seed for random number generation helps ensure that the same random numbers are generated every time the script is run, right? So if I have set a seed, it does not matter. I can write 442 here, or I can write 48777 here. It does not really matter, but it's just for replicability. So if you want to replicate the same results, even when you are using random numbers, you could set the seed. Then we use a function in R called rnorm, and we generate a normal distribution. We have to specify the mean and standard deviation of that normal distribution, right? So we generate this data. I'm pressing Control plus Enter here. Then I can just plot a histogram of this data, right? So the histogram looks something like this, right? This is exactly what is called as a normal distribution. It is also called as a bell-shaped curve because the curve, if you draw a curve from here, it will be bell-shaped, right? So what are the characteristics of a normal distribution, right? The normal distribution is symmetrical. So you can see that on both sides of this peak, the distribution is more or less symmetrical, right? The mean is equal to median is equal to mode. So the mean, median, and mode, all of those are 50 in this distribution, right? So it is a bell-shaped curve, and this kind of normal distribution is the kind of distribution that you will see in normal life in most scenarios, right? So, for example, the marks of the students or the performance of employees or the speed of runners in a marathon, all of these usually conform to a normal distribution. It is one of the kind of data distribution that we see very often in our daily lives, right? So, two characteristics, it is symmetrical, the mean is equal to median is equal to mode. And if you make the mean equal to 0, and if you make the standard deviation is equal to 1, that is something called as a standard normal distribution. Uh, I mean, there is nothing really special about standard normal distribution except for the fact that its mean is 0 and the standard deviation is equal to 1. There are certain other interesting facts about normal distribution also. So, for example, within plus and minus one standard deviation. So, in this case, the standard deviation is 10, right? And the mean is 50. So, within 40 and 60, which is minus and plus one standard deviation from the mean, there will be around 68% of the values lying within this area. If you expand it to two standard deviation, you would find that 95% of the data lies between two standard deviation and 99.7% of the values lie within three standard deviations, right? I'm not going too much into the syntax of histogram and this curve. You could just replicate it as is. That is not important. What is important is understanding the interpretation of these. So in this line, we are just creating a histogram, and in this line, we are creating a curve on top of that histogram, right? This curve is a bell-shaped curve. It is symmetrical, mean equal to median equal to mode. So it's a normal distribution, right? Now we will try and simulate the central limit theorem in the next part of the video. Hope this was helpful. Stay tuned for the next part. Thank you.